Welcome. In this lecture video, we'll discuss how to detect seismic waves and what the instrument involved actually is. So, passing seismic waves cause the ground to oscillate, right? So the seismic waves are literally vibrations of the ground. The first thing to discuss is the different types of seismic waves. Do you remember what these are? Go ahead and pause the video and jot down on a piece of scratch paper the names of all of the different types of seismic waves that you can remember, and if you can remember any specific details about those, go ahead and write those down too. Please do this because if you quiz yourself first, you're much more likely to be able to easily remember the information later. So go ahead, stop the video, and just write down what you already know before continuing. Okay, so hopefully you remembered body waves. Body waves, there are two types, right? So there is the P wave, which is a longitudinal wave. The P wave is made of compressions where material is scrunched together and dilations where it's pulled apart. The particle motion of a P wave is parallel to the direction that the wave moves. So in this example, you can see, hopefully you can see the little boxes are indicating movement along in the same dimension as the direction the entire wave is traveling. An S wave is actually an example of a transverse wave because the particle motion is perpendicular to the direction that the wave is moving. So an example of a P wave that you might see in everyday life is if you took a slinky and you held it sort of vertically and then you just put some energy in and you could see that energy go down and back. If you took, on the other hand, a piece of rope and you quickly put a pulse of energy into one side, you would see that pulse travel down the rope by moving the rope up and down in a direction that's perpendicular to the direction the wave is traveling. Another type of waves that sometimes we just group together is surface waves. There are actually two types of surface waves. There are Rayleigh waves, which make a sort of rolling particle motion, and there are love waves, which make a back and forward particle motion. The difference with these waves, I know love waves in particular might look a little bit like S waves, but you can see that the magnitude of that motion is actually getting smaller the deeper into the ground that you go. And so that's one of the main differences between these surface waves. They're quite large at the surface, but as you get deeper into the earth and there's now sort of a bounding layer of rock above them, they don't have that freedom of motion and no longer exist. So as the name implies, surface waves only exist at the surface, and they actually are the most destructive of any type of seismic wave if we were to discuss earthquakes. Something I forgot to mention about the P waves and the S waves that's actually critically important is that P waves, the compression waves, these can travel through basically any medium, gases, liquids, and solids. Sound is a P wave, for example. And S waves, on the other hand, are shear waves. Shear waves cannot travel through either air or liquids. They can only travel through solids. I mean, if you imagine trying to create a particle motion perpendicular to a wave motion in a bathtub, if you went in and just started going like this, trying to get a wave to go that way, it wouldn't work. You can't shear a liquid. You can't shear air. Okay, so that's pretty important to remember. Okay, how do we measure these things? Well, we use different types of seismometers. These are a little bit simplified versions, but they, I think, do a good job of getting the point across. Basically, you need some sort of object that's going to be more or less stable while the ground beneath it moves. So we have an example of a machine that is capable of measuring horizontal motions and a different machine that's capable of measuring vertical motions. A lot of times these days equipment can measure both in a single device, but it's still common to have single motion devices as well. Okay, so here is an example of a simple type of seismometer that is actually able to record earthquake waves. I personally have worked with the one that's photographed and shown here. Basically what you need is to have some sort of stabilization of the mass. So you have a mass and it's going to move, and when the ground moves, it's going to be set in motion. So you need to dampen that motion so that you end up only recording the ground movement and not the motion of the seismometer itself. So the ground moves, this causes the sort of background area of the seismometer to move. You have a spring of some kind enabling your mass source to stay basically in one place, and you have something to damp that so that there's no feedback between the motions of the ground amplifying the motions of the seismometer. So here are just a couple examples of what the instrumentation might look like in a research setting. So the instrument on the left, this sort of tubular looking, that is a broadband seismometer, meaning it can record a broad range of frequencies, and that's typically used in earthquake seismology. This unit would be buried in the ground, made sure to have very good contact with the ground so that it is very well coupled to the ground. And then you could use it for detecting seismic events like earthquakes. You can use it to monitor for nuclear testing, all these sorts of things. This instrument is incredibly sensitive, and it's going to be able to pick up vibrations from around the globe. Now, another type of instrumentation is the geophone, and this is actually going to be more of our focus in this class because geophones are used in near surface work. Okay, so both of these pieces of equipment are going to record any deviations from baseline, and that deviation is what we term the seismic response. Okay, they both work by converting ground motions into a voltage, right? Something that can be measured by computers, and we can record this to know how strong the various pulses are. How that works, and here's the example of the geophone, is that there is a magnet inside of a coil of wire, right? So this is how it's actually done today versus weights and damping forces. What we have, well, there are still damping forces, it's just not oil. So we have a magnet, and then we have a coil of wire around that magnet. And it turns out that when a magnet moves inside of a coil of wire, that moving magnetic field actually generates an electric field, and that means that there is current running through the wire, and we can measure the strength of that current and use it to tell us something about the motions of the ground. Okay, so for the damping aspect here, that is still happening because it turns out that a moving electric field generates a magnetic field in the opposite direction. So there's actually some physics going on between electromagnetism that's going to be both generating electricity in the wire and damping the movement of our device so that it doesn't just shake out of control and make it impossible for us to record the true motions of the ground. So here's an example of sort of the internal structure of a geophone. And then there's an example of a trace of what we might be recording from this geophone. For more information about how it is that magnets moving through coils are able to generate electricity, see the following videos. Here's just an example of what a seismic survey might look like. More on this in the next chapter. But basically, unlike the case of a broadband seismometer where you just might have one in one location and then another one hundreds of kilometers away, for a seismic survey, you're going to be laying out the geophones at discrete areas, putting your pulse into the ground at one end of the line, and then watching that be recorded at different locations away from the source. Okay, so that concludes this video on measuring seismic waves. Hopefully at this point you can describe in pretty basic terms how seismometers work to record the vibrations of the ground. Also, you should be able to describe each of the different types of seismic waves in detail.